Today to examine and review your PhD defense. So the jury of today is composed of Dr. Fabien Denner, who is a referee of this thesis, Dr. Eric Goncalves, also referee, Dr. Outi Sopunen, sorry, myself, Arnaud Koviak, Dr. Michel Arrigoni, Professor Stefan Zaleski, and Daniel Foster, your advisor. So you have 45 minutes to defend, and then the jury will ask a few questions.
Thank you very much for your kind introduction, and welcome to my PhD defense. Today, I'll be talking about DNS of nucleation and collapse of bubbles which are attached to walls. I want to first address this question that why should we study cavitation? Cavitation bubbles can find plenty of applications in several disciplines uh, where you can find bubbles which can range in different sizes. These can range from a size of a COVID-19 virus to tallest man in the world. Some of these applications are shown in the videos below, where in underwater explosion you find very large bubbles. For surface cleaning, which belongs to industrial applications, you find medium-sized bubbles, and in shockwave histotripsy belonging to medical applications, you find even smaller bubbles. The bottleneck in these operations remain the limited understanding of a cavitation bubble and how it interacts with the surroundings. So today we'll try to address this. First, I want to show you the experiment that I did when I was visiting my parents back in India. I should warn you, you should not try this at home as this can be dangerous. So what I do here is I take a firecracker, I light it up, sorry for that, and I put it into the tank of water and see what we see after is the formation of a cavitation bubble and the flow field that you now see on the screen. The cavitation bubbles can be seen at the time instances which are marked here with the red arrows for more clearer visualization. Clearly, to understand cavitation in more detail, we need to move to laboratory experiments, for which we go to Dr. Michel Arrigoni's lab, where we do the experiments with pulse laser. We focus the laser onto bottom of an aluminum plate, which is kept in a tank full of water, and we observe cavitation from top and from front with high-speed photography. In the left, I show you these videos which are taken from these experiments. What you see here is multiple cavitation bubbles can nucleate, which are attached to walls, and as these can interact among each other, and these can even coalesce. And during the collapse, a single bubble remains, which leads to a peculiar dynamics, which I'll also discuss today. Moreover, when a cavitation bubble collapses, several small-scale features such as high-speed liquid jets, shock waves, and sometimes even light emission can happen, which happens at very small time and length scales, which make it a really hard problem to study, which is probably one of the reasons that it's been over a century that Lord Rayleigh described the dynamics of a spherical bubble, and we are still studying it very enthusiastically all around the globe. What are the questions that we want to address in this PhD? The first question that we ask is, can we understand the heterogeneous bubble nucleation and the microlayer formation using our CFD model? We want to understand when does a cavitation nuclei grows into a large bubble, and when does it form a microlayer, which is the layer of liquid that is trapped here in the middle of the bubble and the solid. The second question that we ask is, can we understand the experimental observations from the collapse of these experiments that I just showed you? It is very common in conventional laser-induced bubbles to see a jet which is going towards the solid boundary, but here we see a jet which is going parallel to the wall and something is going upwards. So we want to understand this. And we also want to understand the dynamics which happen at almost 2 orders of magnitude larger than the bubble collapse time, where we see a free surface jet that is formed, that you're seeing on your screen now, that is formed after at a distance which is very far away from the size of this bubble. The third question that we address is, can we characterize the non-spherical collapse of the bubbles using the energy conservation approach? And the last question that we asked in this PhD is, can we improve the understanding of multiple bubble cavitation? The last part of the thesis was conducted at Physics of Fluids group in University of Twente. Today, I'll answer only the first two questions, and if you are more curious about the other questions, you can always refer to the thesis and keep an eye on the publications that are going to be there in future and also that is published. So how do we answer these questions? We use a combination of analytical and numerical approach. For the numerical approach, we use Bacillus PD solver. This was developed here in our lab by Dr. Stefan Popine and co-workers. In particular, I use Allmark solver in Bacillus, where we solve the compressible form of Navier-Stokes equation while considering both viscous and surface tension forces. The peculiar details of the numerical method were published in Journal of Computational Physics by Dr. Fuster and Dr. Popine in 2018. Here I describe you the equations that we solve in this Allmark solver. We solve an advection equation for interface position. We solve mass, momentum, and energy conservation equation for both of the phases. And then the system is closed by an Stefan gas equation of state. We also need jump conditions to couple the motion of two fluids, for which we specify zero jump of velocity across the interface, which means that we neglect mass transfer effects. Pressure jump is given by the Laplace law, and for the normal derivative of temperature, we also specify zero jump across the interface because we assume an adiabatic process. We also have a contact line in our problem. It is a line where the solid will meet the gas and the liquid phase. A standard non-slip boundary condition for solid is known to produce diverging shear stresses as one approaches the contact line. This singularity is often regularized by using what is called a slip model, where what we assume is that solid can slip, the liquid can slip over solid surface, and this slip is controlled by this parameter called slip length. Along with this, we specify a static contact angle that is implemented using height functions at the smallest grid size. And this model has been used in past to represent the motion of contact line and is shown to be a promising tool to represent this dynamics. Moving on to the problem setup, we solve a Rayleigh problem for spherical cap bubbles which are attached to walls, where the bubble is initially in equilibrium position and the pressure far away from the bubble is suddenly changed. Now, if this pressure is smaller than the equilibrium pressure, the bubble will expand, and if it is larger than the equilibrium pressure, this bubble should collapse. The dynamics of these bubbles can be given by these dimensional quantities, which is the pressure far away from the bubble, the equilibrium pressure, the densities and viscosities of both the fluids, the surface tension, the radius of curvature, contact angle, and speed of sound in the liquid phase. We can define characteristic dimensions and non-dimensionalize our problem such that the dynamics of these bubbles can be represented as function of following non-dimensional parameters. We can further simplify if we assume that the density ratios and viscosity ratios are less important, and we fix these parameters to 10 to the power -3 and -2, and we restrict ourselves in low Mach number regime where the collapse velocity is much smaller than the speed of sound in the liquid phase. Hence, we end up studying the bubble dynamics as function of following four important parameters, which is the pressure ratio, the Reynolds number, Weber number, and the contact angle, which is the only parameter that controls the shape of these bubbles. Alternatively, we also use capillary number and Ohnesorg number while talking about the microlayer formation because this simplify our discussion in this context. And I'll discuss this in detail when I'll be talking about the microlayer formation. For the numerical setup, we do 3D axis metric simulations where we have a square domain. The far away from the bubble, we have outflow boundary condition with constant pressure, which is given as P infinity. The bubble is attached to a wall, which can be a free slip, a no slip, or a partial slip, depending upon a particular case that I'll be discussing during this talk. The boundary is 100 times the size of initial bubble. Uh, so you can see to get rid of any edge effects that can be there in the simulations due to the boundaries. And we also need initial conditions for the bubble where we impose a zero velocity everywhere in the domain. And for the pressure, we solve the Laplace equation to get the initial pressure field. For a limiting case of spherical bubble, you can imagine that if I put a 90-degree contact angle and a free slip boundary condition, then this boundary behaves like a symmetry boundary condition and we can simulate a spherical bubble. Moving on to our discussion on heterogeneous bubble nucleation and in particular the results of this presentation. First, some theory about heterogeneous bubble nucleation. It is known that there can be gas that is trapped in the solid impurities uh, at the liquid solid interface because of the irregularities in the solid surface. And when the pressure falls below critical pressure, for example, by a transducer, these impurities can grow and lead to larger bubbles. These can grow explosively. This is a situation which is called as an unstable bubble. An unstable bubble is well represented with this video on the right, where you will see there are two bubbles. One is smaller in size and other one is larger in size. And as these bubbles rise in this tank, the pressure falls and the larger bubble become unstable and it grows explosively. Whereas the smaller bubble, it remains stable. We can predict this critical threshold by quasi-static theory, where we assume that the pressure is changing infinitely slowly and the radius, the bubble is also evolving infinitely slowly. And dynamics or evolution of such a bubble is given by Laplace law. I plot this Laplace equation here. You see as the pressure decreases, this bubble expands, it reaches this minimum can be predicted from analytically, and it turns out to be a function of only one non-dimensional parameter, that is function of the surface tension, the bubble size, and the equilibrium pressure. This is well known in literature and it's famously known as Blake's threshold, and the corresponding size is known as Blake's radius. We start by predicting Blake's threshold numerically with the DNS. Here I show you the evolution of cube root of bubble compared to the initial bubble, bubble volume compared to the initial volume uh, as a function of time. For different pressures, one for which it's lower than the critical pressure predicted from the theory, and in other the pressure is larger than the critical pressure. And you can see that when the pressure is larger than the critical pressure, the bubble keep on growing till the end of simulation because it's unstable, whereas in the other case it remains stable. Now we can repeat same procedure to get the stability of bubbles with different values of this non-dimensional parameter. The theoretical estimate from previous slide is shown with the dotted curve here, and the numerical results with the points. We see here that for smaller bubbles, there is this difference between the theory and the DNS increases, which is due to the fact that in the theory the pressure decreases infinitely slowly, whereas in the simulation we suddenly decrease the pressure. One can present similar stability arguments for bubbles which are attached to wall. In this case, we imagine that we can imagine that bubble remains as a spherical cap throughout the evolution, such that the geometry of this bubble is controlled by two parameters, which is radius of curvature and contact angle. Now we look into two limiting cases. One is what we call as free slip, where the bubble can move freely on this solid boundary with a constant angle of contact. And the other one is a pinning boundary condition, where the length of contact remains constant and bubble is pinned at the initial location. For these two cases, we can find the critical pressure, which I show here with the color maps. Uh, the the black curve here is an isobar for minus 20 bars, and the first observation that we can observe is that for the free slip bubbles, uh, the threshold does not depend on the contact angle, whereas for pinning boundary condition the threshold increases as the contact angle increases for these spherical caps. We can thus put these two isobars in a same curve, and we can identify three regions basically. In region 1 the bubbles are always stable. In region 3 the bubbles are always unstable, and in region 2 the bubble stability depend upon the how the contact line moves. We verify this numerically by taking a representative bubble in region 2, and we again do the experiment that I showed you previously, and we see that the pinned bubble behaves stably, whereas the free slip bubble behaves unstably. And here I show you the evolution of the interface for these two cases, and I can start drawing my first conclusion, which is that the pinning of contact line acts as a secondary effect that stabilizes the nuclei, and this effect becomes increasingly important as the contact angle increases. Now moving on to second aspect of my study, which is microlayer formation. We want to study the formation of microlayer as function of Ohnesorg number, capillary number, and contact angle. The capillary number is defined for a given set of fluid properties. It's defined with the driving pressure, and the Ohnesorg number is defined with the bubble size. Therefore, we can predict that for a given bubble size given by Ohnesorg number, what is the critical pressure that gives a critical capillary for which these bubbles will become unstable and grow explosively. To start with, we fix the Ohnesorg number to a smaller value. We fix the slip length and contact angle, and we move along this vertical line where we study the effect of capillary number on the formation of microlayer. Note that this regime corresponds to small Ohnesorg, and large capillary regime corresponds to large Reynolds and large Weber numbers. And I'll come back to this also when I'll be talking about the effect of Ohnesorg numbers. Another comment about microlayer formation, that it's truly a multi-scale problem, where one can imagine that at large scale the inertial effects are more important, and close to the bubble the important effects are visco-capillary effects. We start by describing first the dynamics of large scale. Here I show you again the volume evolution as function of time for different capillary numbers, and the time is non-dimensionalized with the velocity, which is an asymptotic velocity of a spherical bubble, which is unstable, and this can be obtained from Rayleigh-Placet model if you plug in zero acceleration into a Rayleigh-Placet model. And we see that after an initial transient, this bubble takes a slope 1, which means that most of the bubble takes the asymptotic velocity of a spherical bubble. And thus, if we have bubble shape at different times, we can rescale these bubble shapes to get a self-similar shape, and we see that at large scale, the bubble shape is grows with the asymptotic velocity, which is UC. One is the velocity of height of the bubble. The second is the velocity of width of the bubble, and the third one is the contact line velocity. We start by looking at the evolution of these velocities as function of different capillary numbers. And as one would expect from the previous slide, that the height of bubble grows like a Laplace bubble and takes the asymptotic velocity, which is equal to the UC, which is the Laplace velocity. For the width, for large capillary number, we see a behavior which is similar to the height, whereas for small capillary number, there is a decrease in this velocity. The more difficult to describe or interesting is the contact line velocity, where we see that at small capillary numbers, this velocity is quite close to the Laplace velocity, whereas for large capillary numbers, it increases and then decays in time. And the difference between the velocity of contact line and the bubble width governs when the microlayer is formed or rate at which the microlayer is forming. We can see this if we plot like velocities in these 3 points as at a certain point of time as function of the global capillary number, that the height and width evolves as the Laplace velocity, whereas the contact line velocity decreases with capillary number, and hence when this difference is large, at large capillary number we see the formation of microlayer, whereas for small capillary number there is no microlayer formation. One can further argue that close to the wall, the more important scale of velocity is given by viscosity and capillary visco-capillary scale rather than the inertial scale predicted by the Laplace model. So we define a local capillary number given with the contact line velocity. And here I show you the local capillary number as a function of global capillary number. And we see that there is a sort of convergence that is reached, and the contact line capillary number doesn't increase uh, as much with the global capillary number, which is more clear if I now plot the contact line capillary number as function of global capillary number. For small capillary numbers, it grows almost linearly, and for large, we see a sort of asymptotic plateau that is reached, and we can predict this plateau if we fix the data with a harmonic average, and the Ca infinity is the value of plateau that one would achieve when the capillary number is very large. We can put all other points into the same curve, which is the height and width. These take the slope 1 because these 2 points evolve with the UC, and the difference between these two gives us the formation of microlayer. This brings me the second conclusion, that the contact line capillary number takes an asymptotic value in the regime where honest org is much smaller than 1 and capillary is the order of 1. We can now again look at the effect of contact angle. This is a rich plot. Here there is a lot that is happening. I show you the contact line capillary number as function of global capillary number for different contact angles. The numerical results are shown with the points, and the fitting with the harmonic average is shown with the dotted curve, and I also show a line with slope 1. So first observation is that for small angles, it's easy to form the microlayer because the difference between these two curves is large, and one reaches this asymptotic value comparatively quickly as compared to large angles. And we can again try to predict the asymptotic capillary number for large capillary numbers, and we see that it varies with the cube of the angle. which is interesting because one can also obtain this from a Cox-Voinov law, which gives the relation of apparent contact angle, which is the angle at certain distance from the solid boundary, and the microscopic contact angle and the capillary number of the contact line. And we can argue that when the microlayer is formed, the bubble becomes flat and this angle tends to zero, and one can recover the cubic dependence of the contact line capillary number on the angle which is put at smallest grid size. This is the conclusion from this slide, which is there. And now to remind you that I was working in large Reynolds and Weber number regime. What happens when I try to change Ohnesorg number for a fixed capillary number? Now I'm moving along this vertical line. And what we see that there are finite viscosity and surface tension or finite Reynolds and Weber number effects that becomes important, and the microlayer formation is suppressed for large Ohnesorg number, as you can see from these 2 points also that the velocity of the contact line becomes comparable with the bubble width. And one can summarize what we observed in the previous slide with this curve, where I show you Ohnesorg versus capillary, and in this region the bubbles are stable, they never grow. In the region where the capillary number is close to the critical capillary number, there is no microlayer, and if one wants to form microlayer, we need to be in a regime where the capillary number is much larger than the critical capillary number. And the color map here is the difference of velocity of width and the contact line velocity as compared to the Rayleigh Placid velocity. Hence, we can start discussing the second aspect of this presentation, which is the bubble collapse. What we asked is to understand the collapse of these bubbles and the free surface jet that will appear after almost 2 orders of magnitude larger time scales compared to the bubble collapse time scale. We start with the approximate theory, which we call as impulse theory. We approximate that the bubble shape at the instant of maximum volume is well represented by a spherical cap. The liquid is at rest at this instant. The density and viscosity ratios are much smaller than 1. And we start looking at what happens at very small times. This can be given by a linearized equation, linearized Navier-Stokes equation, and it's very standard to decompose the solution of this equation into a potential and viscous part. The potential part, the viscous part is important close to the boundary layer, which close to the solid boundary, inside the boundary layer, which grows with the thickness of which grows with square root of time. Sorry. So as I was saying that the viscous part is important within the boundary layer, which grows with the thickness with square root of time, and for large enough Reynolds number and short time, the velocity is majorly governed by the potential flow solution. We can find this potential flow solution from Euler equation. We can do better by assuming the uniform gas pressure and incompressible liquid, and hence take the divergence of the Euler equation, and what we obtain is a Laplace equation for pressure. Here we non-dimensionalize pressure with this formula, and we choose like characteristic scale for density and length. Therefore, we end up with just one free parameter, which is the contact angle, and we study the dynamics of these bubble as function of contact angle. The boundary conditions for this Laplace equation are shown in the figure on the left. And let's start by plotting the non-dimensional acceleration, which is the pressure gradient as compared to non-dimensionalized with the acceleration that you will get for a Rayleigh Placid bubble, for a spherical bubble. Here I show you the ISO contours for this parameter, and in the right you see the value of this parameter along the wall uh, at a distance rs, which is the distance from the contact line. So far away from the bubble, we see hemispherical shapes, and we see that the pressure gradient or the acceleration decays with 1 by r square, which is an outcome of incompressibility condition. But as one approaches the contact line, we see that this acceleration diverges. So why does this happen? Is because of a corner singularity that exists in the Laplace uh, in the solution of Laplace equation when we have mixed boundary condition. By mixed, I mean a Dirichlet and Neumann boundary condition, and the point where these two meet can be singular. There are various solutions which are proposed in literature for this singularity. Here we used this particular solution, which is a series solution with exponent given by this formula, and we see that first term of this series diverges when b0, the exponent for 0th term, is smaller than 1, or the contact angle is larger than pi by 2. So this point is singular when we have a open angle, or with an angle which is larger than pi by 2. And we can verify the existence of singularity in our numerical simulations. We fit the numerical data, particularly C0 and B0, with the first term of the series. And here I show you the DNS results, or the numerical results, which are the points, and the solid line is the theory, and they match well. So we verify that there is a singularity in the numerical simulations. We also can predict the C0, which is the only free parameter, and it turns out to be of the order 1 for all the bubbles. Therefore, with this single free parameter, we can represent solution near and far from the bubble. But can we predict the acceleration along the bubble interface? Which is what I show here. I show the interface acceleration as function of this polar angle, which we call as theta wall. It is the angle which is 0 at the contact line, so it's 0 here at the contact line, and it is pi by 2 at the axial location. The solid line corresponds to the first term in the singularity solution. The dotted points are obtained from the numerical simulations, and we see when the singularity exists, the first term dominates the solution, and we can predict relatively well the interface acceleration from just the first term. Another interesting aspect from this curve is the change of behavior that you see when the angle is larger than pi by 2 or smaller than pi by 2. When the angle is smaller than pi by 2, the acceleration decays to 0, and at the contact line, and at the axial point you see an acceleration which is comparable with the Rayleigh-Placet acceleration, which is the acceleration for spherical bubble. And in the case when angle is larger than pi by 2, we see that it goes to infinity at the contact line, and it's comparable to a0 at the axial location. And one can already start to imagine that what will happen when these bubbles will collapse, uh, and that this bubble will lead to a jet which is going towards the wall, whereas these bubbles with open angles would lead to a jet which is going in the direction parallel to wall. And as they reach the axis of symmetry, there is a jet. There is a stagnation point that appears at axis of symmetry, and we see a jet that goes in the direction opposite to wall. The color map here represents the vorticity. We can compare one to one the experiments and the numerical bubble shapes, which are shown with the red curves. And we see that we can predict very well the dynamics that is happening in these two cases, and that the change in angle can change the direction of jet that can appear. We can still make more, we can take more out of the singularity solution or the impulse series solution If we look at the vorticity that is generated at the interface at small times, and it will diffuse into liquid bulk by virtue of viscosity. If we apply a stress-free condition at the interface, the only non-zero component of vorticity is the gradient of velocity with the theta direction. Here you can see that it is the supposed to be the slope of these curves, and we see that this slope changes when the angle is smaller than or larger than pi by 2. Therefore, in this case, a vortex ring is generated like this, which travels upward during the collapse, and in this case, we see a vortex ring that travels towards the wall and is responsible for cleaning of the solid. This is what happens in these experiments, that when this vortex is strong enough, it can travel to large distances, and what you see at larger times is a jet that is generated at the free surface. Therefore, I reached to another conclusion that the bubble response is very sensitive to the bubble shape at maximum volume given by the contact angle for these spherical caps. And the impulse theory can be used to predict the dynamics of collapse of the bubbles, uh, uh, but it predicts an infinite acceleration at the contact line. We know that we didn't take into consideration the viscous solution. So we ask, can viscous solution regularize the singularity? And here I show you the complete solution which is obtained from Allmark solver from DNS at different instants of time. So blue is the small time and red is the large time. As function of the distance from the wall, which is here. And we see that as the time passes, the boundary layer is generated, and uh, the the velocity is maximum at certain distance from the wall. We can see this shift in maximum velocity in the video above as well. Uh, so now one can try to predict what is this maximum velocity from the uh, impulse theory from the potential solution, which is shown with the black curve. What we do is we take the value of the velocity at a distance which is square root of nu t times which is the this is the height of boundary layer. So we take the velocity at the height of boundary layer, and we try to predict the exponent with which it should grow. It gives us an exponent which is 1 by 2 plus pi by 4 alpha. And we again extract the maximum velocity from DNS and fit this exponent, and we compare the two, and we see a very good match. But the interesting thing here is that this exponent is still smaller than 1. Therefore, even the viscous solution remains to be singular at t equals to 0. So we can look at the effect of viscosity at if further, like what we do here is we look at the collapse of low pressure bubble which are collapsing at under the action of ambient pressure, and the only parameter that governs the Reynolds number is the size of these bubbles, because that's the only free parameter, and we see at around Reynolds of 100. So what I show you here is the maximum velocity that occurs during the collapse as function of these Reynolds numbers. We see at around 100 Reynolds number there's a jump in velocity, and at this point the bubble does not form a jet, and the viscous solution dominates over the potential flow solution. Hence, I can start concluding my presentation. Uh, the gas nuclei becomes unstable when the pressure falls below the critical pressure value predicted by the quasi-static theory, so which is this region. The microlayer is formed when the capillary numbers are much larger than the critically capillary numbers, and the contact line capillary number takes an asymptotic value in this regime, which varies with the cube of the contact angle. For the bubble collapse, the potential flow solution is singular for angles larger than pi by 2. This solution can explain the jetting opposite to the wall, the formation of vortex ring, and the formation of jet at the free surface. And at Reynolds number smaller than 100, the viscous solution dominates, and we do not see any jet formation. For the future perspective from current work, we can try to understand the effect of contact line modeling on the asymptotic growth that I showed you. We can try to look more into the details of vortex ring that is formed during the collapse of bubbles attached to wall. We can also try to understand because like until in this presentation I've showed you results from where the nucleation is decoupled from the collapse. So we can try to look into the bubbles which nucleate, form a microlayer and then collapse, which can lead to very different kind of dynamics and very funny looking shapes. These can be like, this depends on what you want to see. So I see this as a laughing Buddha. Daniel sees this as a Christmas tree, and you can imagine whatever you want to imagine from these bubbles. And with this, I want to thank you for your kind attention, and I'll be trying to answer your questions.
Thank you very much for this very nice presentation. So we'll wait for a few moments for the audience to reach a steady state.